How's it going, everybody? I am here on Monday, May 3rd, and today we're going to introduce our last topic of the semester. We're in week 15 right now. It's our last week of content here. We're going to talk about Introduction to Matrices today, so that we can talk about transformation matrices in our last and next video coming up right here. You should notice that there are no explicit sections in the book that deal with matrices as a general topic. Our algebra textbook does introduce matrices for the purpose of solving systems of equations. While that is one of the very large number of very useful applications of matrices, it's not going to be the one that we're discussing in this class here today because we're not interested in solving equations in trigonometry so much as dealing with concepts or associated with rotation and angles, right? So today we're going to introduce matrices. We're not really going to see any truly trigonometry topics today, but in the next video we're going to see how we can use matrices for trigonometry applications, right? So I do want to kind of emphasize here that matrix operations have like a outrageously huge number of very practical real world applications. Since we're obviously only spending 1 week talking about them, I'm sort of like just cherry picking like one of the thousands of applications of matrix operations that exist out there for us to consider because it's one of the ones that's most closely related to trigonometry. So here's the goal is this problem that I've got stated right here, that if we'd like to be able to solve this problem using matrices by the end of the next video. A triangle is formed by 3 points in space. 1, 0, 4, 1, and 2, 5 are the three vertices of the triangle. What I would like to know is if we took the triangle formed by those vertices and rotated it by 30 degrees in space, what are the new locations of those three vertices right there? That's the question that we want to be able to answer using matrices by the end of the next video. So what we're going to do today is we're going to get all of our definitions and all of our kind of like base computations, like how do you even multiply two matrices together? What does that even look like? Stuff like that. In the next video, we'll say, now that we know how to do these mathematical operations, let's see how we can use them and interpret them in the context of things like geometry related problems like the one that we're expressing right here. So today is a bit more of the doing. Tomorrow, we're not going to get any new operations. We're just going to see how we can interpret the operations that we learned today in the context of some geometry, trigonometry related topics here. So one of the important things that I do want to identify is that this goal problem for us to be able to solve this week right here, we technically are already capable of doing this, right? And I'm going to give you a good reason why we still care to pursue a new route to doing this. So let's just go ahead and do this for one of the 3 points on the vertex, or one of the three vertices of this triangle. So our three locations are 1, 0, 4, 1, and 2, 5, where this triangle is located out there in space. So like I can kind of think of this as being at like 1, 0, 4, 1, and 2, 5. There's like our three locations there of the points on this triangle, A, B, and C. And so what I am interested in doing is rotating this point B by 30 degrees in the plane. And again, we can already do this, but it's going to be really tedious and a lot of work. And I'm going to give you a good reason why we care to make that more efficient here in a second. So I'm going to refer to our new point, our new location, as B prime. It's the adjusted location of B after it undergoes the transformation of a rotation by 30 degrees. So here's what I'm thinking to myself. Currently, B is in an XY format. However, I want to apply a rotation to it. And what you know is that polar coordinates play very nicely with rotations because they're defined by r and theta. So here's what I'm thinking. I currently have an XY location for B. We can convert this XY information into R and theta information in polar because you guys know how to convert Cartesian into polar coordinates. In polar coordinates, it's very, very easy to apply rotations because you just add that amount to the current amount of rotation associated with the point. Then once we've done the rotation in polar, we can convert back to rectangular so that I know those final XY coordinates, all right? So we're going to convert to polar. Perform the 30-degree rotation. And then convert back to rectangular. This is going to be our process here. So let's go ahead and do this. All right, so I want to take the point 4, 1. So b equals 4, 1. So that tells me that x is 4 and y is 1. I want to go ahead and convert this guy to polar. And so the two equations that I know are that theta is going to be the tangent inverse of y over x, which in our case is going to be the tangent inverse of 1 over 4. The other thing I know is that r is the square root of x squared plus y squared, which is going to be the square root of 4 squared plus 1 squared. So doing these two operations, this one I can do kind of by myself right here. It looks like this is going to be the square root of 16 plus 1, which is the square root of 17. So I've got the radius associated with this point. For the other one, I know that I'm going to need to go to a calculator for. I want to find out what's the inverse tangent of 1/4. So let's go get that guy real quick over here in Desmos. Over here in Desmos, I'm going to set myself up to be in degrees. We're doing a degree rotation, so I don't want to get a radian rotation for my polar coordinate here. And we want to know what is the tangent inverse of 1/4. I know I'm in the first quadrant, so I do trust that this number of degrees is appropriate here. And I'm getting 14.04, I think is a good round for that, 14.04 here. So let's head back over here. We can see we're getting 14.04 degrees from our calculator. So for step 2, we're going to do the 30-degree rotation. So I'm going to say theta equals 14.04 degrees. Tells me that, and maybe I'll call it here theta prime to go along with our naming convention where b prime is the new location, b is the old location. Theta prime, therefore, should be 14.04 degrees plus the 30 degrees that we're adding on. So it looks like our new theta is going to be 44.04 degrees. And our radius is just remaining the same, right? We didn't change our radius, we just performed a rotation. So I now have my polar coordinates that are associated with this location in space. So now let's go ahead and convert polar back to rectangular here. So now for step 3, I want to convert my polar back into rectangular form. And so I know that x equals r cos theta and that y equals r sine theta. But I'm sort of thinking to myself, these are the primes that go on theirs now because we're using our new location in space. So this should be that x is the square root of 17 times the cosine of 44.04 degrees, and that y is square root of 17 times the sine of 44.04 degrees. And now once again, we can go to Desmos, and it looks like we'll have our final xy coordinates for this point right here. So we're going to do root 17 times the cosine and the sine of our 44.04 degrees here. So for my two computations here, I'm going to do square root of 17 times the cosine of 44.04. And I also want to do, I'm just going to copy and paste this one down and just change this to sine. And there's our two answers right here. As it looks like our new coordinates are approximately 2.96 for the x value and 2.87 for the y value. So that would be my like x prime and b prime. So I think I would conclude here that b prime is about 2.96, 2.87 after having performed a 30-degree rotation there, right? So, and this is a good general concept associated with performing, oops, sorry, I'm not switching over to words. So there we go. So we got our x prime and our y prime, and I'm just writing that overall as our b prime right there. And again, our big point here is to perform rotations, xy coordinates aren't your friend. Polar coordinates are your friend. So we converted into our more appropriate format, did the operation of rotate by 30 degrees easily in our polar format, then converted back to the original format in which the problem was given to us, which was our xy coordinates, our rectangular coordinates there, right? So not terrible right here. We can do this, but this took me like kind of a bunch of work right here. That was just for one of the 3 points, right? Now, here's the broader thing to realize. So this was possible. However, that was a whole bunch of work. And you should realize that when we're looking at computer-generated graphics associated with movies, with TV, with video games, it's commonly the situation that we want to move the location of a pixel or really thousands or millions of pixels at a time, we want to perform things like rotations or sliding them or maybe expanding them. All of these different types of transformations of a whole collection of points all at once. And we want to be doing this to thousands or even millions of pixels at a time, up to like 60 times per second if that's your screen's refresh rate. So basically that's saying to me, if we need to do this like 60 million times per second, if there's a million pixels that need to get moved at 60 frames per second, that's 60 million times per second. We would have to be able to perform this math right here. This is kind of a clunky process right here. So what our goal is to find a more efficient way to do this, because this is technically doable, but like really slow, right? And again, all of the movie, TV, video games that you ever watch that ever have any amount of CGI in them or computer generated images, all of them are doing, ultimately they want to perform this end product right here. None of them do it this way, because this way right here is a terribly inefficient way computationally. Our goal is to find a much more computationally efficient way to do the same thing so that we can deal with all the points at once. And again, obviously because we're trying to like learn the concept here, we're only looking at 3 points. But remember that every time you're watching like a fancy new movie or playing a fancy new video game, that we're talking millions of points in space that are getting updated like many, many times per second. We have to have efficient mathematical operations to do those processes, or else it's just never going to be able to happen, right? So this is sort of our motivation for right now as to why to learn about matrices. And again, matrices do have like more practical computations associated with them than like any other branch of math. We are looking at one of the like millions of reasons why it matters to care about matrices, but this is one that is closely related to trigonometry. So that's why we're introducing matrices from this direction right now. So let's start talking about matrices. So today we're just going to identify lots of features of matrices and see how to perform calculations with them. Tomorrow we'll see the interpretation of all those computations, right? So today is about the doing. Tomorrow is about the understanding. Okay, all right. So matrix dimensions. First idea right here. A matrix is a mathematical object that has scalar values, right? So just numbers, not like vectors within them, scalar values arranged in a grid. We identify the size of a matrix by the number of rows and the number of columns, and we always will state it in that order so that there's never any confusion when you state what dimensions a matrix has when you're talking with somebody else. This one right here I can see has 2 rows and 2 columns, which is often abbreviated as just cols right there. And so we would refer to this as a 2 by 2 matrix. This guy right here has, it looks like 3 rows and it has 2 columns. So we would refer to this as a 3 by 2 matrix because there's 3 rows and 2 columns. Finally, over here, you should notice that this one only kind of, in a sense, has 1 dimension, right? It's got 3 rows and only 1 column. This is a 3 by 1 matrix. And you should notice that this basically seems like what we've been calling a vector for the last week, right? So vectors and matrices, in a sense, have some overlap in that if a matrix ever has dimension 1 for either its number of columns or its number of rows, then each of those could be referred to instead as a vector, and that would be appropriate. So this is what I would call a column vector, because it only has 1 column. And instead we could write this as 5, 4, 3. And here I would say that this is a row vector, right? So row vectors and column vectors are matrices that have only 1 row or 1 column, depending on what shape we're currently writing that thing as. And by the way, I started to write a comma right here, and I should not, because we don't write commas within matrices when we write them by hand, right? So identifying the dimensions of a matrix, how many rows and columns does it have? It always goes rows, then columns, rows, then columns, rows, then columns. All right, so it's always going to be in that order, and that matters for some computation that we're going to do up here in a minute. So let's start with our easy operations and then go and move on to our harder operations here. So addition and subtraction of matrices. Matrix addition and subtraction is defined very simply. It's just performing addition or subtraction term by term. It's just like what we did with vectors. It's the simplest possible way that you could think to do this here. So I've given you a smattering of sample matrices out here, A, B, C, D, and D. Let's go ahead and do some computations with them here. So I'm going to set up A plus C, and that means I want to add the matrix 3, 1, negative 2, 6 to the matrix C, which is negative 6, 3, 2, 1. And all we're going to do for addition and subtraction is we're just going to do it term by term. So 3 is in the first row, first column, plus -6, which is in the first row, first column, should be giving me -3 as my term in the first row, first column of the resulting matrix, right? So again, we're looking at terms that are in the same location relative to each other in the given matrix, performing the operation there. 1 plus 3 is going to give us 4. -2 and +2 is going to give us 0. 6 and 1 is going to give us 7. So there's our addition between two matrices. Very, very similarly, we can do subtraction in a very similar way. D minus A looks like the 9, 2, 1, 1 matrix minus the 3, 1, -2, 6 matrix. And again, we're just going to do this term by term. So 9 minus 3 is going to give me 6. 2 minus 1 gives me 1. 1 minus -2 is like 1 plus 2, so that gives me 3, and 1 minus 6 is going to give me -5 right there. All right, so we can do these things, again, relatively simple right there. It's just doing term by term operations. Finally, or not finally right here, let's determine A plus B. And so A is the 3, 1, -2, 6 matrix. 3, 1, -2, 6 matrix, and we are looking to add this to the 4, 5, 1, 2, 3, 4 matrix. Now, you should realize that this is going to get a little bit uncomfortable because even if I could do first row, first column is 3, plus first row, first column is 4 to get 7 for the first row, first column over here, what's going to end up happening? Like, what do we even use the 3 and the 4 for over here? It looks like there's nothing really happening. Now, there certainly aren't zeros sitting down there in the bottom for us to do this addition. So kind of our dilemma here is it looks like this is just like me saying to you, hey, what do you get when you do +6? And you should say to me, what +6? Addition is an operation between two numbers. So if I'm trying to take 4 numbers and add them individually to 6 numbers, that doesn't make any sense because we're missing 2 numbers from which to do the addition. So this is an undefined operation right here. And I think we can conclude matrix addition and subtraction requires the same dimensions. All right, so our answer here for this one is you can't do it. It's an undefined operation. Whenever we're performing matrix addition or subtraction, it must be the case that the dimensions of the two matrices match one another. And we can see here we're looking at a 2 by 2 plus and this had 3 rows, 2 columns, so the dimensions did not match in that case right there. Therefore, we do not have a defined addition or subtraction between those two matrices. Finally, we can do this to do some sort of solving operations out here as well. We can solve for the matrix E, which is unknown. We have matrices for A and for C. And so fortunately, we can just do some algebra operations out here. So we've got the matrix A is the 3, 1, -2, 6. Plus this unknown E matrix is going to be equal to the C matrix. And our C matrix up here is the -6, 3, 2, 1. -6, 3, 2, 1. Well, fortunately for us, we can go ahead and perform our algebraic operations just like we would expect, which is that we can, for E, I'm going to go ahead and subtract the A matrix over to the other side here. So -6, 3, 2, 1, minus 3, 1, -2, 6. And now we're going to see that we're going to get -6 minus 3 is going to give us -9. 3 minus 1 is 2. 2 minus -2 is 4, and 1 minus 6 is -5 right there. So we found our E matrix here by solving an equation using the same types of algebraic maneuvers that you would normally use to solve an equation. We can subtract like quantities from both sides of the equation, stuff like that. So not too terrible. Matrix addition and subtraction, nothing too crazy going on out there. Now, next topic, multiplying matrices by scalars. Remember, a scalar is just a number. So this isn't multiplying two matrices together. This is like taking the matrix B and multiplying it by the scalar, the number 3. Our other very simple matrix operation is multiplying a matrix by a scalar. Again, in this case, we simply multiply each term of the matrix by the associated scalar. These are the same four matrices that you saw a second ago. So I can do things like identify what is 3 times b. Oops, I didn't make my thing big enough because b is a big matrix right here. Okay, I'm going to make an adjustment to some of these ones coming up right here because I didn't realize what I did to myself right there. That's okay. So this should be 3 times 4, 5, 1, 2, 3, 4. And all we're going to do is just triple everything that's inside of this matrix right here because we're multiplying by 3. So I'll go to 12, 15, 3, 6, 9, 12. All right. So what I've realized here is by accident I set this up so we get more of our impossible scenarios. You should notice that 2a is going to be a 2 by 2 matrix, but 3b is not going to be a 2 by 2 matrix, so this operation is undefined. So let's make this be an actually defined operation. I'll change that to a c. Similarly down here I included that b. Let's change it to a d, so that's also all 2 by 2s out there, right? So we still have that same exact issue of dimensionality from before. So if I want to find the quantity for 2a plus 3c, that should be 2 times the a matrix, 3, 1, negative 2, 6, plus 3 times the c matrix now, negative 6, 3, 2, 1. This should be 2 times this first one is going to give us 6, 2, negative 4, 12. Oh, Microsoft Word, if you can't stop highlighting that thing, I'm going to freak out. Here we go. And we're adding to that 3 times the second matrix. So this should be what? Negative 18, 9, 6, 3. And therefore we should be getting out when we add these two together. It looks like 6 and negative 18 gives me negative 12. 2 plus 9 is 11. Negative 4 and 6 is 2. 12 and 3 is 15. So there's my 2a plus 3c right there. And as our final computation down here, 3a minus c plus 2d. What I'm going to suggest is you should pause the video for a moment and do this and see if your answer matches mine. So now that you've just unpaused the video, what I would like to show you is that we can use a little bit of technology to help us out with this, and not just some technology, we can use our favorite technology, which is Desmos. So I want to show you guys how this works out here in Desmos. So coming on over to Desmos over here, what you should see is that like Desmos does lots of stuff for us. Like it does other things other than just numbers. We know that it does like our like kind of our verbal, like our trig function, stuff like that. Other things that makes Desmos really useful is that this also handles things like summations. So I use these in calculus 2 a lot. It handles things like integrals, which we use in calculus all the time. So that's really good stuff. The other thing that's good that it handles is matrices. Unfortunately, whereas we type out the word sum to get a summation and it gives it to us, we type out the words for integral, and as soon as I type int, it gives me the integral symbol. What I want to have happen is I want to type out matrix, and it gives me a matrix, and unfortunately that doesn't happen right there. That's just because the matrix component of Desmos is handled in a different place. It's not within the calculator. So to get to the matrix thing that's handled in Desmos, I'm just going to change calculator to matrix. And that's going to take me to a new calculator that Desmos has. So you should notice that the tools that Desmos have is the graphing calculator, which is probably what all of you have used 99% of the time. It also has a scientific calculator and then a very basic for-function calculator. And importantly, it has a matrix calculator, and that's what we care about here. So what I'm going to do is I'm going to define those matrices that we had. So I'm looking at my notes right here, but the matrices that we had were A is equal to, and I'm going to say new matrix, and it just pops up a 2 by 2. Notice if I wanted to give it more rows or more columns, I could click on those things right here. I could click on those buttons, but I don't because we're defining a bunch of 2 by 2 matrices for right now. But I could like click this and make it get bigger or smaller, stuff like that. Oop, 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 oop. Clicking on other things on my desktop here. Oops, oops, oops. So let me click that. There we go. Back down to a 2 by 2. So our A matrix was 3, 1, negative 2, 6. And I'm just going to go ahead and hit enter. And the nice thing is now is that it just knows the matrix A. So I'm going to do the same thing now for C and for D, since those are the ones that we were using here. So C we said was equal to, I'll click new matrix. C was negative 6, 3, 2, 1. and I'll hit enter. So it now knows that value of C. I can now use C in my computations, and I'll do D equals new matrix, and that was 9211, and hit enter. So it now knows, it learned the values for A, C, and D right here. So let's go back and like double check that this does work, 2A plus 3C, and then we'll do our final one down here. So 2A plus 3C, let's do it over here in our matrix calculator. 2A plus 3C, and I'll hit enter, and it's giving us negative 12, 11, 2, 5. Negative 12, 11, 2, 5 is exactly what we got when we did this guy 1 second ago over here. So that seemed like that works. So now let's see if we can get Desmos to give us the 3a minus c plus 2d here as well. So 3a minus c plus 2d. I want 3a minus c plus 2d. And it's giving me 33, 4, negative 6, 19. 33, 4, negative 6, 19. All right, so again, to use the matrix calculator over here in Desmos, you need to first define your matrices by saying like A equals B equals C equals D equals whatever matrices you've got, whatever names you're giving them. Then you can come down here and do operations with the defined matrices that you've defined up above right there. Really, really convenient for us there. And at the end of the day, what you should have already learned so far about matrices is that a lot of the computation associated with matrices is tedious. It's going to end up amounting to tons of addition, subtraction, and multiplication all over the place. And that's it. And those are not hard things to do. So our goal is more to understand what are the computations, that we know what our calculator is doing, and then in our next video to be able to interpret those computations for some meaningful purpose out there, right? And by the way, did I get that? Yes, okay. So also pretty easy. The operations we're really here for today, though, is multiplication between two matrices, right? So we've handled the super easy stuff. Addition between two matrices, subtraction between two matrices, multiplying a matrix by a scalar, like just a number, 2, 3, -1, stuff like that. All relatively easy things for us to go ahead and do there. And we've just seen that we can just use Desmos as a basic matrix calculator for us, so that we're not just sitting around doing addition and subtraction and constant multiplication all day, which is really boring, right? So let's see, the little bit more exciting one is what we want to see, multiplication between two matrices. But before we do that, I want to go look at one other matrix operation that's going to be relevant to our discussion in the next video, which is the determinant of a matrix. This one's a little bit weirder because this one isn't going to be an operation between two matrices. This is an operation on a single one matrix. And it's a bit weirder, right? So since matrices can be massive, and just as a very, very brief statement I'll say to you, you should be wondering things like, I don't know, I think that a lot of people kind of like miss on how crazy technology is these days. And I think one of the crazy things that's been crazy for a long time and is still crazy now is that you can go and do a Google search, and within like a tenth of a second, it will return like 53 million relevant results to you. How in the world is it doing such a massive search in such a short period of time? And the answer is Google is holding all of its search results and whether or not a page contains some certain type of information in matrices, and they're doing matrix multiplications to end up determining those answers for you. All right, so matrices, a lot of the most useful matrices that are out there are just huge matrices, millions of rows, millions of columns, holding insane amounts of data. And doing matrix operations with them can recover for us the data that we want, right? So because matrices can be massive, and as I just described, some of the most important matrices in your life are things like Google, the algorithm in Netflix that predicts for you that you're going to watch, the Great British Bake Off next week based on the fact that you watched whatever you watched last week out there. This is literally all matrix operations that are happening under the hood to tell you these things, right? So it's, on Netflix, there's tens of thousands of shows. It's comparing what you watch against what millions of other users watch. That's a matrix that's going to have tens of millions of columns and tens of thousands of rows. And they're going to do matrix operations to do things like make predictions for what you want to watch, stuff like that. So since most of our most meaningful matrices can be absolutely massive, what we often want is some form of summary information rather than dealing with the like billions of numbers that are going to be in those matrices. Can we come up with one number that is sort of a descriptor of the contents of that matrix, a single number summary? One way that we can do it, there's lots and lots of different summary types of pieces of information about matrices. One of the most important ones is what we refer to as the determinant. Um, for now, we're just going to calculate it, and we're going to talk about what it does for us in one setting tomorrow in our next video, or not tomorrow, in our next video, right? So we're just going to do the calculation, and even more than that, I'm going to get even more specific with you than that. We're also only going to discuss in this class here the determinant of just a 2 by 2 matrix. And when you want to go talk about determinants of other sized matrices, you will learn about that in your appropriate class that deals more broadly with matrices in general. For our purposes here today, since we're only going to talk about two-dimensional graphs, we're going to talk about 2 by 2 matrices, and you'll see why those twos are related to each other tomorrow. All right, so here's the three statements about the determinant of a matrix that I care for you to know in this class. There's a ton that's still out there to be learned about determinants, but for our purposes here today, these are the three things you got to know. One, the determinant is only a defined quantity for square matrices, right? So we saw that 3 by 2 matrix up above. There is no defined determinant for that. It's not a square matrix. A square matrix has the same number of rows and columns, an n by n matrix. The determinant of a 2 by 2 matrix, if we just list the terms as A, B, C, and D, will be AD minus BC. So that's your formula right there for the determinant of a 2 by 2 matrix. It's that we're going to take the product of the two numbers on the downward facing diagonal, and we're going to subtract off the product of the two numbers on the upward facing diagonal there. The third thing that you should know about determinants is that they get super tedious to compute as the size of the matrix gets larger. Even doing the determinant of a 4 by 4 matrix by hand would take me like 5 minutes to do. It's really obnoxious and tedious. It's not hard. It's just a bunch of multiplication and addition and subtraction, but it's just like a ton of it, and I'm not going to sit around and do it. In general, nobody really sits around and does determinants by hand, with the exception basically of 2 by 2 matrices. This is kind of always expected that you can do this by hand. And when I say by hand, I really kind of mean just like in your head, because this is not a terribly difficult computation for us to do right here. So anytime that we get to determinants of larger matrices, and again, even a 3 by 3, I would go to the internet and ask for the determinant rather than do it by hand. Even though I know how to do it by hand, when you go to take linear algebra or something later, you'll absolutely learn about taking determinants of larger matrices out there. And it is valuable that you know how that computation is done, but most reasonable people just let a calculator of some form do that for them. So let's go ahead and look at some examples of determinants. And aside from just computing a single determinant, I'm going to show you some examples of when I experienced determinants of matrices in some of my higher level calculus classes. So the next two examples below the one you can see right here are both problems that I have solved in a calculus class this semester. All right, so these are relevant to your mathematical future here. So compute the determinant of the matrix 3, 1, negative 2, 6. So what we're thinking here is I'm thinking of this like our A, B, C, D general matrix right here. And what we've been given is that the determinant of this matrix, and I might call this matrix A right here, I would then write that the determinant of matrix A is going to be, and what is our formula? A times D minus B times C. So it's my down diagonals product minus my up diagonal product. So in this case right here, it looks like we're going to get 3 times 6 minus BC is going to be 1 times negative 2. So in this case, it looks like we're getting 18 minus negative 2. Minus a negative is addition, so it looks like we're going to get 20 as our final answer right here. And it just occurred to me that I didn't test it, but I'm certain that it's going to work out. Uh-oh, sorry, I'm realizing my computer is about to die right here. I must have unplugged it. Let me get that guy plugged in. There we go. Okay. All right. So this determinant of a matrix is certainly an operation that's going to be given to us in our matrix calculator in Desmos. So let's see. Let's go back over to Desmos. The 3, 1, negative 2, 6 is what we had already called A here. We can see that it's defined right there. There's A is 3, 1, negative 2, 6. So let's go ahead and just hit enter right here. And what I'm seeing here is there's a button right there at the bottom that says det. And that's exactly what we are interested in here, the determinant. And I'm also positive that you could just literally type out det like I did right there of A. And you should see it's telling us 20 exactly like we just computed by hand right there. So the determinant is also something that's handled by our matrix calculator right there. And again, I did determinant of A because we had already defined A to be that 3, 1, negative 2, 6 matrix as we had already used before right there. Okay, Cool, cool. So our calculator works, our by hand computation works. So now let me show you some situations in which you can't get away with just using a calculator to solve this thing, where you do have to do some by hand work associated with determinants. And again, this example and the next example are both examples that I have that have cropped up naturally occurring matrix scenarios in one of my calculus classes this semester here. So determine the value of A that makes this statement true right here. I want to know, what does A need to be so that the determinant of this matrix is equal to 4? All right. Well, I can go ahead and compute the determinant, and I'm remembering here, I always like to think of my determinant as the down diagonal minus the up diagonal right there. So I sort of have visualized these groupings like that in my mind. I'm going to erase this. Well, yeah, I'm going to erase this for right now because it just makes this very cluttered looking. But that's like the thing that I'm picturing in my head, is the downs minus the ups is what I say to myself when I'm doing my determinant. So it looks like our determinant of this matrix right here is going to be 2 times A, that's the product of the down diagonal, minus the product of the up diagonal, minus -2 times 1. Oh, come on, man. You got to stop with that highlighting stuff, Microsoft Word. That's just unreasonable. So I'm looking at here, that's equal to 4. I'm looking at here, 2A plus 2 equals 4. And so I can subtract 2 from both sides and get 2. And it looks like, kind of boringly, it looks like A would need to be equal to 1 for the determinant of that matrix to be equal to 4 right there. So that's one problem that has naturally arisen in a calculus problem this semester. This is the one that actually crops up over and over and over and over and over again in one of my calculus classes in differential equations, is to solve this equation where the determinant of a matrix is equal to 0, and where there is a subtraction of a variable on both terms of the main diagonal. This is, as to why this is going to happen, don't worry, just go take a few semesters of calculus and you'll be there. But this exact equation right here, I mean, change the numbers around. The structure of this thing right here, I have my calculus students have probably done this 50 times this semester. This is a very, very, very important calculation that arises in some calculus context here. So let's go ahead and do this. So it looks like my matrix here is going to give me a determinant of, I want the down diagonal product minus the up diagonal product. So I feel like this will be 3 minus x times 1 minus x. That's my down diagonal product, minus 2 times 4 is equal to 0. All right, so here's what I'm seeing. I'm going to multiply out these terms. I'm going to multiply out these terms. This should be giving me 3 times 1 is 3, minus x for the middle, minus 3x for the outside, and plus x squared for the lasts, and then minus 8 here equals 0. I'm going to rearrange these terms so it looks like a quadratic that I actually care to deal with. X squared, it looks like that's a minus 4x. And my constants, 3 minus 8, is going to give me a -5 is equal to 0. This looks like a factorable quadratic to me, so I think I could factor this as x minus 5 and x plus 1 is equal to 0. And that's going to tell me that my solutions here are that x is 5 or -1. Those are the two values of x that would cause the determinant of this matrix to be 0. Again, when you go to take your linear algebra class or whatever class in the future where you learn a lot more about matrices, what you're going to learn is that the determinant of a matrix being 0 is a very special scenario that we want to be able to identify when does it occur. So anytime that there's variable components within a matrix, it's very often important to say, by the way, which values of those variables will cause the determinant to be 0? We want to kind of watch out for those types of scenarios. Sometimes they kind of ruin the math that we're doing. Sometimes they like show us the answer to the problem that we're trying to solve right here. Right now, we're just doing the computation, right? So there's some determinant related ideas right there. And again, I will only ask you in just this class for just the determinants of 2 by 2 matrices, but there's certainly value in larger matrices determinants as well. I just would never do it by hand. I would always use a calculator to do it. And again, determinants are only defined for square matrices only, where there's the same number of rows and columns out there. Okay, so determinant, a little bit of a weird idea, and we haven't seen why we're doing it yet. We'll see one of the many, 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 many reasons that we care to know about the determinant tomorrow in the next video. But for right now, it's just a really simple, a little bit of multiplication, a little bit of subtraction right here. If some variables get involved, you might need to do a little bit of algebraic solving for a variable associated with that determinant computation. All right. So finally, the thing that we're kind of really here for, this is sort of the most important thing for all of our discussion that we want to have tomorrow about why are we doing all this matrix stuff, is we need to be able to do some matrix multiplication. So here's the thing to remember. When we defined the dot product between two vectors, we saw that it was different than how we defined the sum of two vectors. The multiplication and the addition didn't pan out the same way. We didn't just do a term-by-term multiplication the same way that we did a term-by-term addition, right? So when we added together two vectors, like a 3, 1 plus 5, negative 2, we did just get the term-by-term sum, meaning first term 3, first term 5, so sum first term would be 8. Second term 1, second term negative 2, so add those together and second term is negative 1. That is how addition worked out, right? For multiplication, it is not the case that when we did the dot product here, we did not do that. This was very much not equal to 15 comma negative 2. We did not perform term by term multiplication. That's not how that works right there. So notice that these are different from one another. Instead, to find the dot product, we found the sum of a term by term multiplication, right? So instead, when we did our 3, 1 times, and when I say times, I mean with the dot product of 5, negative 2, we instead did this 3 times 5 plus 1 times negative 2. And that gave us 15 minus 2, which was 13 there. Right? This was our more appropriate way to do this. So the first thing I want to say to you is recognize that addition doesn't work the same as multiplication in vectors or matrices. We've seen that addition works out super easily. It's just like you'd hope it would be. You look in the same slots with both of the things, the vectors or the matrices, you add or subtract those together, boom, you got the resulting thing. Not the case for multiplication right here, right? We did something different. The difference is going to be the same with matrices as it was for vectors. We're going to be dealing with dot products rather than dealing with term-by-term multiplication. So to see how this matrix multiplication works, you can think of rows and columns of a matrix as being their own vectors. And we're just going to take lots of dot products. So here's some things that I'm thinking. You could just think of this first column of this A matrix as a vector. Similarly, it would also be reasonable for you to think of this first row of this A matrix as a row vector. We know how to perform dot products between vectors, and we can always think of any one row or any one column of any matrix as a vector sort of contained within that matrix. And we're going to do dot products between vectors where we're thinking of the rows and the columns as vectors within a matrix here. So we're going to start by looking at the general product of two 2x2 matrices, but we're going to talk about what other types of ways can we make this multiplication happen. Does it just have to be two 2x2 matrices? The answer is no, but there are some restrictions here. So here's what's going to end up happening, right? And I'm going to kind of read the phrasing in this bottom statement down here, and I'm going to write a sentence that goes along with what we're seeing right here. So a couple small things, first of all. First, let's talk about the notation right here. You should see that we've got these subscripts on all the A's right here, that this is just like our A matrix times our B matrix right here. Typically the case that we always use capital letters for matrices, and then the same lowercase letter represents the term within the matrix. Since this term right up here is located in the first row and the first column, this is A sub 1, 1, first row, first column. This guy right here is located in the second row. Remember, it's always rows first, then columns second. So second row, first column is where this guy is located right there. So we would call this A21. This guy's in second row, second column, so it's A22. Don't confuse your 2 1s and your 1 2s. Remember that row is always the first piece of information, column is always the second piece of information. So this one right here is in the first row horizontally, second column vertically right here. So I'm just going to make one statement right here. This is like my example statement of how to do one of the computations we need to do. If our goal was just to find the term that's in the first row, second column of this overall resulting matrix right here, we're going to take the dot product of the first row of A and the second column of B. So the location that the term ends up in the final matrix is exactly determined by which vectors you use to take the dot product of between matrix A and matrix B. This is one of those things that I think is hard to describe in words. I do want to get some words out there, but this is much, much easier for us to see if we just kind of do this by hand. So as our first matrix multiplication, I have the exact same 4 sample matrices right here. Let's go ahead and do our first matrix multiplication here. So I'm going to multiply the matrix A, 3, 1, negative 2, 6. Sorry, I don't want to just run out of room and be upset with myself later. I'm going to write that a little bit smaller here. 3, 1, negative 2, 6 times D, which is 9, 2, 1, 1. So what we're going to do is we're going to do lots of different dot products right here. So if I want to find the term that is going to land in the first row, first column, we're always, and again, referencing this phrasing in this paragraph right here, we're always going to look at the rows of the first matrix and the columns of the second matrix. So I'm going to take the dot product here of the first row of the first matrix with the first column of the second matrix. So what that should be is it should be 3 times 9, right? That's 3 times 9 plus 1 times 1. That's what the dot product would be of the vector 3, 1, 9, 1. If I want to find the term that's going to go in the slot below it right here, this would be the second row, first column. So I'm going to take the second row of my first matrix, dot product with the first column. So this should be negative 2 times 9 plus 6 times 1. If I want to get the first row, second column, that's the guy that goes right here. It's in the first row, but it's in the second column now. I'm going to take the first row of my first matrix and the second column of my second matrix. That should be 3 times 2 plus 1 times 1. Finally, to find row 2, column 2 of the resulting matrix, I'm going to take row 2 of the first matrix, dot product with column 2 of the second matrix. Negative 2 times 2 plus 6 times 1. And now I'm just going to do the math right here and see what we get. It looks like this should be 3 times 9 is 27, plus 1 is 28. Here I'm going to get negative 18 plus 6 is going to be negative 12. 6 plus 1 is going to be 7. Negative 4 plus 6 is going to be 2. So it seems like that should be our product of the matrix multiplication, A times D. What's going to happen is after you've done a bunch of these in your head, you're going to come to, or excuse me, sorry, I said that wrong. You're going to see that once you've done a bunch of these, you're going to realize that you can probably do some of this math right here in your head. I've multiplied together about 1 billion matrices in my life. So this is something that I can do as mental math now because I've done this row times column thing over and over and over, where we do the term by term multiplication row by column, but then add those results to get the one number that goes in that slot right there. Certainly this is a bit of a weird operation, so I do want to go to Desmos right now and confirm that A times D will in fact give us this result. So let's pop over there real quick. Again, I've already defined A and D here. I've already got our A and our D that we just used 1 second ago to do that matrix multiplication. So I'm good to just come down here and just do what is A times D. And you are seeing here 28, 7, negative 12, 2. And 28, 7, negative 12, 2 is exactly what we got when we did this guy by hand. So it looks like our by hand computation exactly matches the computation that we are seeing here out of Desmos right there. So again, very, very helpful because this matrix multiplication is honestly a little bit inconvenient to do by, it's not terrible. And again, it's one of those things where like, I basically expect everybody to be able to do everything by hand with 2 by 2 matrices. And as soon as we get into things that are bigger than that, it's like, let's just use a calculator instead. But that's small. It's faster for me to do this matrix multiplication in my head than it is for me to go to Desmos and type it all in. So I'll still do this manually here. So now let's look at another interesting thing here, which is that And let me just move this around a little bit, shuffle some terms here, shuffle some. So I'm just trying to keep on keeping our reference matrices on screen right here. So we just did A times D. Now what I want to do is do D times A. And here's the thing that you should be thinking to yourself right now. This is like the matrix equivalent version of me saying to you, hey man, what's 3 times 2? And you're going to tell me 6. And then I'm going to say to you, but wait a minute, what's 2 times 3? And you're going to say, why are you asking me this? It's 6, right? Same thing. I just asked you what's A times D. I'm now asking you what's D times A. Let's go ahead and do it here. So D times A, it looks like is 9, 2, 1, 1. That's D. Times A, which is 3, 1, negative 2, 6. Let's go ahead and do the matrix multiplication. So row 1 times column 1 is going to give me, and I'm just going to write this one out now, and let's see if you can follow this mental math in my head right here. Or maybe I'll just write a little bit less. 9 times 3 is 27, plus 2 times negative 2, that's really a minus 4 right there. So that's my first term. I did the dot product of the first row and the first column. And if you want to see it, write it out for yourself. The dot product of the vector 9, 2, dotted with the vector 3, negative 2 right there. Right? For my upper right term up here, I should do row 1 times column 2. 9 times 1 is 9. 2 times 6 is 12. Lower left corner should be row 2 from the first matrix, column 1 from the second, because we're in row 2, column 1 in this position. 1 times 3 is 3. 1 times negative 2 is negative 2. And finally, row 2, column 2 is going to come from dotting row 2 with column 2. Row 2 of A, or row 2 of D with column 2 of A. So 1 times 1 is 1. 1 times 6 is 6. And what does it look like we're getting here? I'm seeing 23, 21, 1, 7. And you should be comparing it to this answer that we got a minute ago and seeing we didn't get anything close to what we just got in our previous computation. Let's go verify that we did our math right in Desmos and do D times A over here. "23, 21, 1, 7. 23, 21, 1, 7. It's exactly what we got right here. So it looks like Desmos agrees with us that there's something a little bit weird going on with matrix multiplication. It seems that while with regular multiplication, 2 times 3 is equal to 3 times 2, that is the commutative property, matrices do not enjoy such a property. You cannot change the ordering of multiplication and keep the same numbers here. So I think a thing that we should be concluding over here is that matrix multiplication is not commutative. AD is not equal to DA. Order matters for multiplication. Now, up above, we saw that when we did like addition between matrices, we just added term by term. So that means that we could have swapped the order and things would have still worked out. So matrix multiplication is not commutative, but matrix addition and subtraction is commutative just like you'd want it to be. The matrix A plus the matrix B is equal to the matrix B plus the matrix A. But multiplication, that got ruined right there. It looks like order actually matters when we do appropriate orderings, or when we do our orderings of our matrix multiplication. So let's look at a couple more now. Let's look at A times B and B times A. These will be our last direct multiplications that we'll do here. We're still using these same defined ones up above right here. Let me scroll my screen just right. Let me get to right there. So there's our AB and our BA that we want to do. So let's go ahead and set them up, see if we can do these guys right here. And again, you should be pausing the video, trying this by your hand right here, trying this by hand by yourself, because we just want to see, like, are you visualizing this the correct way of how to do this math? So an important thing to notice here is that we're now talking about bringing in one of these non-square matrices, right? So 4, 5, 1, 2, 3, 4. So is this even going to work? We just checked a second ago and we saw that addition between two matrices that are different sizes aren't going to work out. Does multiplication between two matrices that are different sizes, is it going to work out? Well, if it is, then what I need to do, for example, is to get, for example, my 1 term that's sitting right in this slot right there, what I would need to do is the dot product of row 1 and column 1. So let me say this here. To find this term, we would need to do, and I'm just going to, oh, these are A and B, nice. Row 1 of A dotted with column 1 of B. I would need to do the dot product of row 1 of A, which is 3, 1, dotted with column 1 of B, which is 4, 1, 3. This is undefined. Dot product requires two equal size vectors. So it looks like our answer here is that this is undefined. And the reason why is because the dot products don't work out together, right? We just tried to take the dot product of a two-dimensional matrix or vector with a three-dimensional vector, and that is not a defined quantity. When we defined the dot product, we said, listen, every time you do a dot product, the two vectors had better be of equal length, and these are not right there. So it seems like AB is an undefined quantity here. And so what I think we should do is we should go ask Desmos if it agrees with us. Notice, by the way, in Desmos, we only have defined A, C, and D so far. We skipped B, so I need to define it. 4, 5, 1, 2, 3, 4. A very creative matrix on my part. So let's go ahead and define it here. B. Oop, 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 oop. All right, let's define it here. B is the matrix 4, 5, 1, 2, 3, 4. So I'm going to do new matrix. I need to give it a whole extra row because I actually had 3 rows. This is 4, 5, 1, 2, 3, 4, right? 4, 5, 1, 2, 3, 4. 4, 5, 1, 2, 3, 4. Okay. So I'm going to go ahead and hit enter. And I can ask it, by the way, just to confirm what is A, what is B. So it's got the correct A and B right there. It still remembers them. And if I do A times B, it just gives me the little error thing right here. And what does it say? Cannot multiply matrices with incompatible dimensions. Now, here's the thing I'm thinking. I like the way that, by the way, this is like the first time I've ever seen this. I discovered that Desmos had a matrix calculator about 20 minutes before I started doing this video, and I was like, oh, awesome. And so I haven't even seen this yet here. The way that Desmos is phrasing this right here leads me to believe that there are possibly some compatible dimensions different than the incompatible dimensions. So it seems like there was a issue here, and it had to do with the fact that this, with our number of rows and number of columns, didn't match up somehow. So you should notice that the next question that I'm asking you to do here, we just asked what's A times B, and we determined what was the answer. Well, the answer was literally is that it was undefined. That's not a defined operation. But now I'm asking us, can we do B times A? So let's go ahead and take a look at what's happening with B times A here. So when I want to do B times A instead, 4, 5, 1, 2, 3, 4. And the question is this even going to work? 3, 1, negative 2, 6. So now you should notice that once again, if my goal is to find this like upper left term right there in the first row and the first column, that would require me to do the dot product of the first row of B, 4, 5, dotted with the first column of A. Well, that seems to be no problem. Two terms right there. So it seems like this one might work out, or at least I should say, I think I can at least get the first term. It looks like there's going to be at least some of this is defined. Maybe we're going to get to the end and realize there's something screwy with the fact that these aren't both the same dimensions here, but I think we can at least get started. Let's just see what happens when we do this, okay? So first row of B, dotted with the first column of A, 4 times 3 is 12. Plus 5 times negative 2 is negative 10. So we can get our first term. What about this upper right one right here? Well, this should be the first row of B times the second column of A because it would be in the first, or sorry, this should be in the first row second column, first row of B, second column of A, because this position right here is first row, second column. So this would be giving me 4, the dot product of 4, 5 with the vector 1, 6. So 4 times 1 is 4. 5 times 6 is 30. Okay, I got that term. Let's see if we can keep going. Now the second row of B, dotted with the first column of A, should put us in the second row, first column, which would be this slot right here. So that dot product will give me 1 times 3 plus 2 times negative 2. That's 3 minus 4. Next up, second row of B times second column of A. Second row, second column places us in second row, second column. That dot product is going to give me 1 times 1 plus 2 times 6. That's going to give me 1 plus 12. And it seems like I should say finally down here now, 3, 4 is the final row, so it should help us get the final row of the resulting matrix. It looks like I want that term from both the first and second column, so we've got 2 dot products to do, one with the first column, one with the second column. So 3, 4 dotted with 3, negative 2, that's going to be row 3, column 1, row 3, column 1, that's going to place us right here. That's 3 times 3 and 4 times negative 2. That's going to be 9 minus 8, 9 plus negative 8. And as our final slot over here, row 3, column 2 is going to place us in row 3, column 2 over here. 3 times 1 is 3. 4 times 6 is 24. So it seems like I was actually able to do all of the multiplications, all the possible dot products that are out there. And now I'm just going to do my addition to clean this up, and it looks like I'm going to get 2, 34, negative 1, 13, 1, 27. It seems like I just was able to do B times A when A times B wasn't even defined. And that's a little bit weird right there. So it seems like there's some dimensionality things that we're going to need to watch out for here. So we're going to talk about that in 1 second. Let's just go to Desmos and confirm our B times A answer right here. So over in Desmos, I'm going to click on my new slot here, and we want to check out what's B times A. And what do you know? It is giving us a matrix that has 3 rows, 2 columns here. And what are our numbers? 2, 34, 2, 34, negative 1, 13, negative 1, 13, and 1, 27. 127. So it looks like we got the exact same result as Desmos got from doing B times A. And it looks like Desmos also agrees that A times B isn't even a defined quantity. Doing this A times B is the same thing like you asking me what's 7 divided by 0. There's not a number that's equal to. It doesn't make sense to divide by 0. It doesn't make sense to multiply the matrix A times the matrix B. And let's look and see what's a crafty little rule that we can use to judge when is this going to happen here. And the important thing is, and I want to come back to what Desmos said here, remember that what Desmos was telling us was that the reason it couldn't do A times B was because it had an issue with the dimensions of the matrices, right? It wasn't like the numbers were an issue. It wasn't like we literally did division by 0. It was that they couldn't multiply the matrices because of some dimension problems between the two matrices here. So let's go ahead and take a look at the dimensions required for our matrix multiplication. So what we just learned is that there's some dimensionality restrictions here. You can't just multiply literally any 2 matrices together. It's not necessarily going to work out. Because we're always going to take the dot products of rows and columns, we need some numbers of rows and some numbers of columns to match up. The other thing that you should see here that's absolutely not at all obvious was that when we did this multiplication of a 3 by 2 matrix times a 2 by 2 matrix, it gave us back a 3 by 2 matrix. How would you know that this wasn't going to give us a 2 by 2 matrix or some other dimension matrix out there? So the real question is, what dimensions do we need? What are the rules for the dimensions to even allow the multiplication to happen? And then if it's allowed to happen, how do you know what dimension matrix you're going to get out on the other end? How did we know that we were going to get a 3, 2 here on the back end over here? All right. So let's take a look at what we just saw right there. Let me just do that right there. So it does turn out it is pretty easy to identify what these rules are going to be. For you to do this like very, very, very easily right here. All we've got to do is identify how many rows and columns is each matrix going to have, right? So let's remind ourselves some features of A and of B. So A had 2 rows, 2 columns, and so we refer to this as a 2 by 2 matrix. B had 3 rows because it was extra tall, 2 columns, and therefore we refer to this as a 3 by 2 matrix. So when we try to do things like A times B, we were doing here, let me get some colors here, we were doing a 2 by 2 and a 3 by 2, and this didn't work out. The reason we're going to see that this isn't going to work out, here's your super easy check for yourself right here, is this. These two dimensions need to match. The inner two, when you write them in the order that you're doing your multiplication, A, B isn't defined because the inner two dimensions are not equal when you write them in the correct order. Man, I just can't get my colors the way I want them right now. AB don't match. Right, so anytime you're looking to do a matrix multiplication, remember that order matters for matrix multiplication. Remember also that we always write rows first, then columns second when we're indicating the dimension of the matrix. So when you write the dimensions of the first matrix times the dimensions of the second matrix, if these two inner ones don't match each other, it's undefined and you don't even have to make any attempt at looking for that matrix multiplication. On the other hand, if we are doing B times A, you should now notice that when we write our dimensions, B was a 3 by 2, A was a 2 by 2. Well, now you should see that our inner dimensions do match. And so therefore, this is a legal multiplication right there. BA is defined because the inner dimensions match. Now the other part of this, hopefully you can play this little visualization game right here, is I'm now asking the other question. Since the dimensions match, we can do the matrix multiplication. But the other question is, what will the resulting dimensions of the matrix be? We saw up here that when we did a 3 by 2 times a 2 by 2, we got back a 3 by 2. So do you see anywhere that 3 by 2 crops up when we write out this little bit of dimension math right here? And that's from our outer dimensions. And that inner and outer is kind of a weird phrasing on my part right there, because it's really just like relative to how we're writing them next to each other. But this is always our nice thing, is if I'm ever asking you, hey, is this matrix multiplication defined? You can always just write down the row by column of the first times the row by column of the second. If the middle two numbers are equal, it's defined. What's the dimension of the resulting matrix? You can just grab the outer two dimensions and put those together, and that's what it's going to end up being right there. So it's really easy to tell once you see the little trick that's associated with it right there, right? So inner two matching determines if it's defined. What the outer two are the dimensions of the resulting matrix if it is defined, right? So that's where that 3 and that 2 come from there, right? So kind of weird, but not too terribly difficult to sort of follow that rule in a sense. So what we really want is we're going to end up doing a whole mess of matrix multiplication in our next video. So it really, really matters that you know, when is matrix multiplication defined? Is a matrix multiplication that we propose even legal? Is it going to have a defined quantity? If so, what do we expect the dimensions to be of the output matrix, right? Those are two really important questions that we need to be able to answer right there. All right, so as our last idea for today, this one will be really nice and easy right here. Let's wrap up today by looking at a very special matrix. And let's go ahead and perform the following matrix multiplication. This one is going to take us a while because these are 3 by 3 matrices. Now you should notice, by the way, real quick, that this is 3 by 3 times 3 by 3. So I'm noticing here that the inner match, so it is legal. I'm also noticing that the resulting matrix is, so I'm going to say here, this is legal. And this says to me resulting matrix is also 3 by 3. All right, right? So that's the kind of math that we did a second ago. Since the middle two match, we can do it. The answer is going to give us the outer two, 3 by 3 right there. So I'm thinking to myself, I can just go ahead and plop out for myself a 3 by 3 matrix here. I know I'm just going to fill up 9 slots in my 3 by 3 matrix. Let's see if we can do the mental math in our heads. Now this is going to be harder because our dot products is going to be a 3-dimensional vector and a 3-dimensional vector. So we've got more math to do right there, but I think we can work through it because look at how many zeros are in this matrix and look how many ones are in this matrix. So let's see here. Our first row, 1, 2, 3, dotted with our first column, well, we're going to get 1 times 1, which is 1, 2 times 0, which is 0, 3 times 0, which is 0. So the only term that survived is the 1 times 1, which gave me 1. First row, second column. I should be getting the first row dotted with the second column to go in the first row, second column position here. To do that in my head, I'm going to get 1 times 0 is 0, 2 times 1 is 2, 3 times 0 is 0. So the only one that didn't get multiplied by 0 is the 2 times 1. So I'm going to get a 2 right here. Next up, we're going to get 1, 2, 3 dotted with 0, 0, 1. 1 times 0 is 0, 2 times 0 is 0, 3 times 1 is 3. So the only thing that survived is 3. You should see something special happening right here. Also, I just couldn't avoid scrolling further, so I'm assuming you've all read the bottom of the page as well right now. What you should see is happening here, and I'm going to do a couple more. Row 2, column 1 will end up in row 2, column 1 right here. 4 times 1 survives. 5 and 6 each multiply by 0, so they go to 0. So all we get is 4. 4, 5, 6, dotted with 0, 1, 0. 5 times 1 is the only one that survives. 4, 5, 6, dotted with 0, 0, 1. 6 times 1 is the only one that survives, right? And to continue on, you should see that we're just going to get 7, 8, 9 again on the bottom row down there. So it seems like this matrix right here, this matrix with the ones and the zeros, is a very, very, very special matrix. It is the matrix, the only 3 by 3 matrix that you could ever multiply another 3 by 3 matrix with and get the exact same thing back again. So we refer to any square matrix. All of these have to be squares for this special case right here. A square matrix that has all ones on what we refer to as the main diagonal, top left to bottom right, and all zeros everywhere else, is what we refer to as the identity matrix, because when you multiply by the identity matrix, you keep your identity. You're the same as you were before at the end of it. The identity matrix should be able to be applied on either side. Remember that matrix multiplication is not necessarily the same when you do A times B, B times A. In fact, it's almost always not the same, A times B, B times A. Since the identity matrix leaves you alone, A times I is going to be I. It's also the fact that I times A is going to be I. So we refer to the identity matrix right here. We just use the capital letter I to generically denote the identity matrix. And it's sort of like the matrix equivalent of the scalar number 1. It's the number that you multiply by if you don't want anything to change. So if you were going to do some multiplication but you didn't want any change on the other end, the only thing you can multiply by is this identity matrix. All ones on the diagonal, all zeros everywhere else. In general, people don't worry too much about notating like dimensions for the identity matrix. We always just sort of, it's not like we say I subscript 3 by 3 or something like that. It's always assumed when you attempt to multiply by an identity matrix that it is of the correct dimensions for the matrix it's multiplying right there. And so what you should take away from this is that computation associated with this matrix, the identity matrix, is super simple. It's literally the thing that says leave it all alone. However, we are going to see that it's going to help us sort of interpret some of the things that we're doing in the next video. So this identity matrix, while it is sort of boring computationally, it does have meaning for us when we come to interpretation, when we come to comprehension for its purpose in the next video here. The 2 by 2 identity matrix, 1, 0, 0, 1, is going to be something that's kind of interest of us to talk about, like what is that actually representing? Why does that keep things the same? All right. So that's going to be kind of one of our key ideas in our next video, is interpreting why does multiplying by that particular matrix keep everything the same right there. That's going to be one of our big questions in our next video. So what we did in this video, I just want to kind of review what we just did right here. We saw our problem. This is still our goal. Our goal at the end of our next video is to be able to answer this question, but I want to use matrix operations rather than doing this big slog of a bunch of conversion work out here, because this took me a bunch of work, and that was just for one of 3 points. And in the real world, this is happening for like millions of pixels, for like every frame of every TV show and movie and video game that you watch or play, right? Like, we need to be able to do a way more efficient computation than doing all this work here, and we're going to do it in terms of matrices. We know that it's important. We now saw by the end of the video especially that it's very important that we can identify the dimensions of a matrix. We always indicate the number of rows first and the number of columns second. We saw that addition and subtraction of matrices, as well as scalar multiplication, was super easy. You just sort of lay them on top of each other, add or subtract the terms that are in the same slots. Scalar multiplication, multiply everything by that scalar. Those are the easy ones. The harder, okay, sorry. We also discussed the determinant of a matrix, which we saw no interpretation of whatsoever today, except that I claimed to you that it's sort of like a summary piece of information about the matrix. We saw some computations that are straight up that you could do in a calculator. We saw some computations that aren't going to be able to be done in a calculator because they involve solving for a variable, so expect some of those. And again, tomorrow when we do our interpretation day, we'll see how do we interpret one way that we can interpret the determinant of a matrix when we look at our transformation matrices tomorrow. And finally, our big idea today, the one kind of hard thing for the day, is doing matrix multiplication. This is something that is always a little bit of a tough one for people to get over the first time they see it. It's one that I hope is obvious to you, has plenty of places where it's easy for you to make small mistakes, which is a little bit unfortunate right here. But I mean, you know, we're gonna do the best that we can here. And so we've also seen though that we can have Desmos help us out with this. So I'm showing you that you have a calculator for a reason. So it is very important. The two things associated with matrix multiplication are you need to be able to judge, can it even be done, which we saw depends on matrices dimensions matching their inner two dimensions. Here we had an inner dimension of 2 and an inner dimension of 3, which didn't match, so we were undefined. Here we had an inner dimension of 2 and an inner dimension of 2, so they did match, so we were defined. You should be able to identify what will the resulting dimensions of a matrix be, which is just the outer two dimensions, and then you need to be able to actually do the matrix multiplication by hand. I absolutely expect that all these matrix multiplications that we did here, you should easily be able to do these by hand for sure if you didn't have a calculator. All right. Finally, we've identified that the very, very special matrix that sort of is the matrix representative of this scalar number 1 is it's the only number you can multiply. It's the only matrix you can multiply by, where at the end of the multiplication, you have the same thing that you were originally started with, right? So it's called the identity matrix because after the multiplication is done, you have retained your original identity. We're going to interpret this guy tomorrow in a very practical way as well. So today was our doing day. Tomorrow is our interpretation day, but I also want to emphasize what I've emphasized like 10 times now, which is that tomorrow's interpretation day is one of like a billion different very practical uses of matrices. It's not the only thing at all. It's just the one thing that I immediately think of when I think of trigonometry related matrices, which is why we're covering it in this class right here. So I will see you guys in the next video where we're going to discuss transformation matrices, matrices that will transform a set of points in the plane. And we're going to look at all the different types of transformations that we can graphically perform on two-dimensional objects. And the one that we are interested in, because this is trigonometry class, is a rotational transformation. And so we want to build a transformation matrix that will apply a rotation to a set of points for us. That's our ultimate goal in the next video. So I will see you guys for our final video of the semester, which is transformation matrices in the next video. Have a good one, everybody.